The
Live.
broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. We're just about ready to start. We've got about 1 minute till the top of the hour, so we'll give a few more people a chance to sign on. I see a few more coming on. So hang tight for about 1 minute. Okay, we'll go ahead and get started, and good afternoon or good morning, depending upon where you are. I'm Sheila Stephenson. I'm the CEO for One Spatial Inc., and I'm joined today by Kevin Siegwart, who is our principal consultant with One Spatial Inc. And so we're going to share some thoughts today on how using the One Integrate set rules engine instead of tools can help you not only drive greater efficiencies in your data management through automation, but also greater accuracies. So I promise this won't be death by PowerPoint. We only have a couple of slides to share with you just to sort of lay the groundwork for those of you who aren't familiar with One Spatial and what we do. So to give you a little sense of who we are, while we may be newer over here in the US, we started over 45 years ago out of the Cambridge labs in the UK. And we have focused ever since our inception on data management. And as you can see, there's a wide variety of industry sectors that we focus on. In reality, everybody has data these days, and so we find ourselves working in quite a wide array of industry sectors. But as you'll see today, we'll be focusing on transportation as one of our primary industry sectors, as transportation and some of these other industries that you see here, they tend to rise to the top with regard to usage of our tools simply because they have some oftentimes a little bit more complex data challenges, and the need to integrate with a lot of more different data sources is prevalent in these industries. So to give you a little sense of who are our customers, it's those customers that do have some of the more looming data challenges, some of those who are managing really large sets of data. And so, and out of our UK offices, we service Ordnance Surveys, Ordnance Survey Ireland, Ordnance Survey Great Britain, also a number of very large utilities, transportation entities, for example, Network Rail. And then also on the global front, we have Google, although that we're actually working with Google over here in the US for their real estate worldwide services. And then other US customers that we are working with are a number of the federal agencies, again, dealing with larger data sets such as NOAA and the US Census, who uses us for integration of the MAF Tiger data from some 3,200 plus entities across the US. And then also more recently a contract with Federal Highways to help with the integration of the HPMS submittal data, and then also some other validations. And as you can see, a number of US DOTs have started using our capabilities to help them with a variety of different data management challenges. And so I'm going to pass it over to Kevin Siegwart now, who's going to explain when we talk about data management, what are the three kind of categories we group that into. And then he'll jump right into sharing with you a number of the different capabilities. And again, we'll focus on transportation today, but we also, as I mentioned, really work with a wide array of other types of data pretty much across the board. So Kevin, I'll pass it to you now.
All right, thank you, Sheila. And for anybody, if you guys have questions, feel free to type the questions in the GoToWebinar information thing. You can see there's a question section, so feel free to ask questions, and we'll leave some time at the end of the presentation to go over some of those questions that you may have. So as Sheila was mentioning, we focus on data management solutions, and our flagship product is One Integrate, and that focuses on three main aspects of data management, and that's data validation, data integration, and data enhancement. The One Integrate product is a rules engine where you can define the business rules of your data and will automate the validation of that data. This can reduce a lot of the time-consuming aspects and the subjectivity of having a manual QA/QC process. Whatever doesn't conform to those business rules gets flagged as what we call non-conformances. Then there's the data integration piece. So when we're doing the data validation, we don't just validate one individual table or one individual data set at a given time. We can validate across the entire enterprise. So this may be working with multiple different GIS type databases, geospatial databases. Like for example, you may have a transportation database and some sort of land management database. We can validate across that to make sure that your center lines are lined up with your boundaries. But then we can also start to bring in other information from other throughout the rest of your enterprise. So for example, we can bring in data from your business intelligence systems or your asset management systems that are non-spatial related, but you could bring that in and start doing these validations across the entire enterprise. And that even includes bringing in other types of data like CAD data. And lastly is data enhancement. So as you're bringing in these data sources, you're getting a better picture of the quality of the data, the amount of time that it takes to update the data. With that information, you can start to define the business rules for how to correct the data. So when it finds those issues, it can automate the cleansing of that data. This is more than just cleaning the data. You can even create new data based off of all the information that you're bringing in through these variety of sources. And then lastly is we can do things like conflation. So Sheila mentioned that the US Census is one of our customers, and we're doing a conflation effort where we're conflating those 3,500 different data providers' data up to a central master repository. And to do that, we're doing things like conflation efforts and change detection to determine what's changed, how much it's changed, and whether or not it should be pushed into that data set. So with that, I'm going to do a couple demonstrations. I have about 4 or 5 demonstrations highlighting a lot of these different capabilities that this product provides. For example, we're going to start with doing some validations against some road centerline data in the state of New York, and we're going to do some geometric and road type validation checks, some integration checks, and automated corrections. So with that, I'm going to flip into my first demonstration. So here we have 2 sets of data. We have a street segment data set, which is the orange center lines in the map, and we have a township, which has the township boundaries. So I'm going to flip over to my One Integrate tab, and we're going to run some validations on this data set. So there's 3 different rule sets that I'm running on this data here. We're running the essential geometry checks. These are a set of rules that we provide out of the box with our One Integrate product. It checks for typical geometric issues that we find in geospatial data. Things like duplicate features, duplicate vertices, kickbacks, and spikes. We're also going to be we also have some road checks. So these are validation rules that are more specific to the transportation industry or road centerline data sets, checking for road names, making sure we don't have overlaps, checking to make sure roads aren't contained within other roads, some overshoots, undershoots, like connectivity checks, and checking the postal codes. And then lastly, we're doing some integration checks. We're checking to see that are my streets not crossing town boundaries? Are the streets labeled correctly with the right township name based off the town that they're within? And checking along the boundaries if a road shares a boundary, whether or not the left and the right town is attributed correctly. So when we're doing these checks, we're doing geometric checks and attribution checks, but then we can also do geometric and attribution checks at the same time. So in this check for road bifurcation, it's checking for what we call bifurcations, where you have 3 segments meeting with the same road name. And the reason why we want to check for issues like this is that this can cause havoc if you have like an LRS-based system. So within those 2 minutes while I was explaining those different rules that we have here, we were able to validate 20,000 features across about 18 different rules. That is about 350,000 validations that we performed in under 2 minutes. The reason why we can process this much data is that we actually take the data, extract it from whatever client we're using or database we're using into our object-oriented disk cache that's designed in a way to do these quick feature-to-feature transactions, enabling us to process through large amounts of data extremely quickly, not running into the typical memory resource issues that you see with other types of GIS and other types of database systems. So in the map itself, we're pinpointing where these issues are occurring. We're also reporting on how well the data map to each individual rule. So we're recording green means good. It means there's 0 nonconformances. Orange is where we have some nonconformances. And then if we had some significant issues with the data, we would see some red dots over here. Luckily for us, we don't see any red, so we don't have too many major issues, but we do have some issues here. And then if I look over in my contents tab, we're pinpointing on the map where these issues are actually occurring. And I just also have some bookmarks here just to speed up the process of seeing these issues. So we're going to go ahead and take a look at this spike. Notice how we're pinpointing the exact location of where that spike is occurring on the linear feature. This is important because we've had some customers like NOAA where they would be doing their data validation using third-party software before they were using OneIntegrate, and they were finding that it would tell them that there was an issue with the feature, but it wasn't telling them where on the feature these issues were occurring. So if they had miles and miles of coastline and they had to go through and pan through a feature to find where these issues are occurring, it could take them 20, 30 minutes, an hour to find where these issues are occurring. So much so that their editors started to break protocol, delete the features, redraw the features, losing all of that rich metadata and history associated with that feature. But now, since they're using our product, the OneIntegrate product, they now can quickly find where the issue is occurring, fix the issue, move on to the next feature, and not break those editing protocols that they were doing before. So making it a lot easier for the editors to do their job more efficiently and quicker. So here's an example of a kickback here. This is we're pinpointing exactly where that kickback's located. We're flagging where we have a short road. So we're saying that any road that's less than 9 meters less than 9 feet is being flagged as a short road. This is where we have an overshoot. The road is just slightly overshooting the other roads. Here's an example of an overshoot and an undershoot. Here we're flagging where we're missing a postal code. If I take a look at this feature here, we can see that the left postal code is null, which is why it's being flagged as a nonconformance. Here's an example of a street crossing over the boundary of a township. And then this feature here is being flagged because the actual township name is attributed incorrectly. So if I look here, it says my left city town name should be Brighton, my right city town name should be Rochester. If I look at the actual underlying feature, we could see the township is actually supposed to be Rochester. So the left and right should be Rochester, not just the left. So now that we've flagged where all these issues are occurring, we could go through and we can manually correct each individual issue. And this could take, especially for our extremely large data set, this could take months to fix. Or we can define in the rules, when we find these issues, how can we auto-correct them? So we have some example fix-up rules that we have over here, and I'm going to fire those off. So the first set of fix-ups that we're going to perform are my essential geometry fixes. So just like we have the essential geometry checks that we provide out of the box with the OneIntegrate product, we also have the essential geometry fix-ups. These will fix those duplicate features, duplicate vertices, smooth out those kickbacks and spikes. But then we also have some custom rules that are defined for fixing the data. So for example, we're going to align our features that are not connected. So within a specific tolerance, we can define which features should be updated and how they should be updated based off of that tolerance. So in this case, we're going to say my township gets the highest priority. Then we're going to align my streets to my townships. Align my streets to my townships, and then align the streets to themselves. And then lastly, we're going to say that if a street is contained within a town, we're going to update that town name to be the proper attribution. So now that we've run those fix-ups, we can go back and let's take a look at those results. So I'm going to go and take a look at where that spike was. Notice now that that spike is missing. Just to highlight that it actually has been updated, we'll pull in an example data set that was the before data set. So we could see what it looked like before and after. See how we just removed that vertice. We fixed this spike. Where we had that overshoot, we fixed that overshoot. Where the street was crossing, see how we can no longer see the township? That's because we're now completely aligned with my township boundary. This is what it looked like before. And then lastly, we also updated the attribution to be correct inside of this particular street segment. So if I look here, we should now see that my left city town name and my right city town name are now attributed correctly. Now let's flip over and take a look at what these rules actually look like. So this is the rule authoring environment. This is where we actually perform the editing or creation of our rules. We can create new rules or edit existing rules. So for my road checks, this is a check where we're checking the street name is not equal to null. This is fully interactive. I can choose which layer I want to validate against or which data set or table. In this case, we'll use the street segment. It brings in the entire schema, so I can choose which attribute I want to validate against. And I can say how I want to validate. In this case, I'm saying a street name shall not be equal to null, or we can change this to maybe an empty string. And we can build on this, so we can make this as granular as of a check as we like. So in this case, I can say it's not equal to an empty string, and it's not equal to null. We can also do other types of attribution checks. In this case, this is where we're checking the postal code value. We're saying that for all my street segments, we're going to test within a range, and we're going to say that my left postal code should be somewhere between 500 and 15,000 as a postal code value. And that's the valid range of postal codes within the state of New York. But what you'll notice here is that my left postal code is stored in the database as a string. So if we wanted to compare a string to an integer to determine whether it's in a specific range, we can't just do that with a string. So what we have to do is we have to convert it to an integer. And we can do that using what we call our built-in functions. So this allows us to change the value or configure the value in a way based off of the built-in functions. So in this case, I'm converting the string to an integer so that I can do the comparison. We can do things like other numeric checks or other numeric functions or mathematical functions, like you may want to round a particular value. We can do string functions. So for example, if there was a leading space or a ending space, we can trim it. We can get substring values. Or if we're doing string comparisons, like we do in the case of conflation efforts, like with the US Census, we can use functions like sound like, and this determines whether two strings sound similar. So you can compare two row names to see how similar they sound. Or we can also use other string similarity functions like the Jarrow-Winkler or the Levenshtein distance model, which determines how closely two strings resemble each other. Another example rule we have here is where we're checking for bifurcations. This is where we're looking at across two different street segments, and we're saying that if a street segment must only intersect one other street segment where it intersects the start of the line segment and has the same street name. So just like we can apply functions on top of numeric values and string values, we can also do geometric functions, like get the start of a line segment or get the end of a line segment or a whole host of other geometric type functions. And we'll get into this a little bit later, but we can even also get information about the measured values in that particular line segment. Oops. So for the next demonstration, I would like to show you how we can do change detection, where we can compare geometries and attribution to determine what's changed between two sources of data. And we find that, when we're working with, at the country level, like with the US Census or the NOAAs of the world, that they're getting data, collecting data from different data providers, and they have to do some sort of change detection to determine what's actually changed from what the data provider has submitted them versus what they have in their master data set. And we find this paradigm that this paradigm actually goes down to the state level, where the states are getting data from the counties, and at the county level, where the counties are getting data from the cities. And most of the time, whatever the parent organization, the schema of the parent organization is typically not the same as the data providers. And the reason for this is that they're doing their own type of workflows, using their own applications, and the data is designed in a way to work with those applications, not necessarily designed in a way to be pushed up to the parent organization. So most of the time you have to do some sort of schema change to make sure that they're matching schemas, and then you want to perform some sort of change detection. So we can do that using our OneIntegrate product. So I'm going to flip back over to my application here. And this is some work we did for a county in Texas, Collin County in Texas. They have 3 different layers here. We have a city boundary. We have the road data for the entire county. And then we have a city that's submitting new data and submitting it up to be integrated inside of the county data set. Now, in the past, the way that the county would deal with this is they would say, okay, here is my boundary for my city. Let's clip out everything that was in our base data, delete it, and then bring in whatever's in the city data set in. Now, when you're doing this, you're going to lose all the metadata associated with the individual features that already exist, all the history information. And not only that, is that along these boundaries of the city boundaries, you have issues with connectivity, so that you're not going to have proper alignment between your cities, across city boundaries. So what we want to be able to do is, instead of just clipping that data out and having to manually go in and edge match all of these data sets, we want to just determine what's actually changed based off of a specific tolerance. And if it is changed outside that tolerance, we want to just submit those edits in. Now, before we want to do that, we want to actually match. We want to make sure that the schemas are the same. So right now, these 2 data sets are in different schemas. So the first thing I'm going to do is I'm going to do some schema mapping. Let me find my rule set. So the first thing we're going to do is my schema mapping, and it's going to remap my schemas so that they are now following that same schema. So when I do that, I now have a layer in here that's just representing the standard schema. Now I've also only grabbed data that's within my township boundary. And then now that we're dealing with the same schema, we then could perform our change detection. So how we do the change detection is we're going to compare the base data, which is my county data, with the incoming city data. And we're going to use a tolerance. So we're going to say, are there any features within a 15-foot tolerance? How much do they represent of that 15-meter tolerance? How much do they intersect? Do they have the same bearing? So are they moving in the same direction? And then we're going to also do string comparisons on the street names to give us a value on how well they match from the county data to the city. And then we do the same thing from the city to the county. And then with that information, we can build proposals for what changes have actually occurred inside the data set itself. And these will be, what features have been added, what features have been deleted, which ones have had some sort of attribution change, or which ones have been reshaped. And once this writes out, give it another few seconds. We then can take a look at those proposals. So these were all the proposed changes that we made to the data set. Things that are orange are matches, so nothing's going to be changed. The geometry hasn't changed within a specific tolerance, and the attribution's the same. Things that are red are where we have deletes. Things that are teal are where we have an attribution change, and green is where we have new features. So if we take a look at where we have this delete over here, if I turn on my base and I turn on my input data, we can see how this area has never been built out. So that's probably why it's being a delete. We also have an example over here of where we have some sort of scalar change or an attribution change. So if I select these features, let's take a look and see what is actually changed in this data set. So we'll just look at what's selected. Let's move this up a little bit. If I come over here to the row name, we can see that this row name is CR 148. This row name is County Road 148. That's why it was flagged as a attribution change, is because these two were different, but the geometries were the same. We also have an example over here on the left side where we have some adds and deletes, and these are because it was outside the tolerance. So it was outside that 15-foot tolerance, so it was being flagged as a add and a delete. Now that I have my proposals, we can take a look and we can say, well, we're only interested in the ones that are proposed. We don't want to see anything that is rejected. We can reject it based off of how well, what our tolerances are, and so forth. So in this case, we're just going to look at those changes. So we could see here, these are the different changes that we're going to make. And then we can push those changes into the source data set. So apply those proposals. And it's going, so basically it's going to delete these features. It's going to update the attributes of the ones that were the attribution changes and apply any other adds. So now if I come back and I turn on my road-based data set, we come in here, we should see that this, where that delete was, oh, getting some refresh issues here. There we go. Okay. Sometimes it caches in the map, but anyway, you can see how it was deleted out of here. And then if we come over to where there was that reshape, which was, I believe, this guy right here. If I select this feature, we should see now that it's been updated to CR 148 from County Road 148. So we are able to apply the attribution changes and the adds and deletes. So these rules were built using road data, but we've done similar conflation efforts with NHD stream data, with parcel data, with electrical data, and a variety of other different data sets, using basically the exact same logic, just using different attributions, doing comparisons of different attributions and different scale ranges. So as we're dealing with a variety of these customers that are these parent organizations that are collecting data from data providers, we found that a lot of times the way that the traditional workflow was that the data providers were submitting data to these parent organizations via FTP. The parent organization would be, maybe busy working on, putting out some other fires and maybe not getting to the data right away. Once they would get to the data, they would look at it. They would find that there was some sort of issue with the data. They would go back and contact the data provider and then tell them, oh, these are the changes that you need to make to your data set before resubmitting. Well, since that time that the data provider submitted, it may have been a month or 2 months, and the data's already changed. So it makes it really difficult for the data providers to update those changes if there's been some sort of big lag between the time that they submit it and the time that they're getting these results. So what we wanted to do was provide an application for our data providers as they're submitting data up to the parent organizations to get instant feedback of what the quality of the data is. Does it meet the business needs of the parent organization? And then notify them what needs to be changed and where those changes need to occur. And that is with our One Integrate data gateway. So let me just show you how this works. So what we're going to do is we're going to log in, and I'm going to log in here. Bear with me. Depending on who I log in as, has a set of rules associated with it. So each individual data provider or people within that for that data provider has a set of rules. We then can take the data, submit the data into the data gateway. It's going to upload that data set in order for us to run the rule set against the data. Once it's uploaded, we can view that data to make sure that everything has been loaded correctly. So we can see that, okay, all my data is there. Then we can run my rule set. So it's going to run the essential geometry checks and the road checks in this case. So these are very similar to the rules that I showed you in the first demonstration, doing those essential geometry checks and my road checks. Notice how as soon as the data provider submits the data up and runs it, they get the results. They can see where they have issues with the essential geometry checks and the road checks. And they can see that, okay, well, looks like we need to do a couple little fix-ups here. We can view the results inside the viewer itself, in the data gateway itself, and it's going to show them where there's some sort of issue. So for example, we can see here we're flagging that we have some sort of connectivity issue here. We can see that looks like the road segments aren't actually connected. But we know that typically you want to be able to, the data providers want to be able to make these changes in their source data set using whatever client they're used to using. So what we provide the ability to do is download the information. So if they submit the data as a shapefile, they'll get the data back as a shapefile. If they submit it as a file geodatabase, they get it back as a file geodatabase. And lastly, if they submit it as some sort of CAD-based file, they'll get it back as a CAD-based file. And then in this, they can then take that data and bring it into their client so that they can go ahead and perform their edits as they see fit. See, this layer here is just a shapefile, and this was the road data set that they submitted. And they can see where all the issues are and go through and auto-correct whatever go through and correct whatever they need to correct. Now, while these data providers are submitting the data, we're also getting metrics on the state of the data at any given time. So we're also taking, we're listening for these validation checks and charting how the data is proceeding over time. So we could see how many non-conformances each individual data provider has versus the number of features. So we get a number of non-conformances versus features. We can view it over time, view it by individual rule, and we can even chart the progress over time by provider. So we can see the state of the data at any given point. So for the next demonstration is related to around field collection. Now, when we go out and we are doing field collection, we notice that there's a lot of potential issues that can arise from doing your data field collection. A lot of times you're sending out people in the field that aren't necessarily geospatial experts or GIS analysts. They're going and they're collecting lots of information, and they're having to add all this extra attribution, which may be able to be inferred by features or objects around. They're doing a lot of different spatial operations that seem excessive. A lot of that requires a lot of manual cleanup afterwards. These aren't geospatial experts. They're not using tools that are traditional GIS tools to do those advanced types of editing. And also, there's no sort of validation occurring in place. So if they don't enter something correctly, it requires the field collectors to go back out in the field the next day and to recollect more data if they're missing something. So what we found is we have a product called One Integrate for ArcGIS Mobile Edition that can help with a lot of these issues. It can validate while they're out in the field, reducing those costly return visits. And then we can also auto-populate attribution and features to reduce the time in the field so that we can basically auto-cleanse the data, just like we were doing before, but this time it's going to be happening as these edits are occurring on the mobile device itself. So with that, I'm going to pull up my device. Just bear with me real quick while I connect. Okay. So I'm pulling up my mobile device. It should come up now. Here we go. All right, so what we're going to do is we're going to open up a collector for ArcGIS. I'm going to go into my web map for collecting. In this case, we're going to collect street sign data. I'm sorry, speed limit sign data, I should say. And I'm going to go, let's just come down here and we're going to create a new speed limit sign and we'll say it's right. Let's zoom in a little bit and we'll pinpoint that right there on the map and we'll submit that edit. And then maybe I'll enter a couple more. So let's go ahead and let's go into F Street here. Oh, I zoomed in too far. Let's create another one. Let's see, where was I at? Oh, and we'll create another one right here. And this time I'm going to make sure that I put in my speed limit because I forgot to put in my speed limit sign before. We'll say it's 25 miles an hour and submit that edit. Now you'll notice that the first edit that I created right here, we have a red X on the feature. The reason why we have a red X here is because the feature itself didn't have the proper attribution. So if I select this feature here, we're going to get two notifications. One, it's saying that it doesn't have a valid speed on the thing. So it's saying that either there's a null value or a 0. What we're also doing is we're validating it against features that are inside of the map itself. In this case, we're not matching the speed category of an underlying data set. So if I take a look at the street data, we have two different street data information. We have my local DC information, and then I also have a third-party data source, the here data, that has information. So if I take a look at that data set here, we can see that the speed category is saying it's a speed category of 6. That means the speed limit should be somewhere between 20 and 30 miles an hour. Because our attribution is not attributed that way, it is not being flagged. It's being flagged as a nonconformance. Also, if I look at my DC street data, we have a lot of information like the street ID, the street name, and the quadrant. So when I take a look at this particular feature itself, let's go take a look and edit my feature. We're going to notice that all of that attribution actually got populated on the fly based off of the underlying data. Now, if I come in and I actually enter my speed limit, when that edit gets posted to the server, it's going to validate again. And if it now conforms to those rules, that red X should disappear. While that's updating, if I take a look at this other feature here, we can see, oh, this one hasn't updated yet. Let's see here. Sometimes, let's try this one more time. There you go. You could see that it just needed to refresh. You could see that all the attribution was populated besides the speed limit because that's what I entered in manually. So this can reduce a lot of that time-consuming aspects of having to go in and manually enter the street name and all that other information that can be easily inferred by features around it. We can also auto-validate the data based off of those features, so making sure that the speed limit signs are the speeds are attributed correctly based off of the underlying data. Oops. So the last demonstration before we open it up to questions is validating your LRS systems. Now, a linear reference system is typically a tabular without actual geometric values inside of the tables itself. So more of a non-spatial tables. But what they do have is they have a begin LRS and an end LRS value, which represents the start or the end of the asset with a mile or kilometer marker value. So if it's at the beginning of a road, it might have a begin LRS of 0, and if it goes for 2 kilometers, it would have an end LRS of 2 kilometers. Then we have GIS data, which in the GIS, the geometries are encoded with what we call M values or measure values. Those are the actual distances of the road segmented in the road segment or the route segment in the real world. So what we can do is we can use this rules engine to validate the LRS and the GIS-based system, making sure that the assets actually exist within the GIS and making sure that they're not missing assets in my LRS. So basically comparing the LRS to the GIS and the GIS to the LRS. So with that, let's show you this example. So we're going to come over here to my map. Now in this map, we have some road segment data. If I take a look here, we can see for this road segment, we have a road name, and this is actually in Puerto Rico, so this is in Spanish, but we have a road name, so this is PR 146. We have some information about, this is just telling us what the length of the road segment is. Now, inside the geometry itself, for every one of these little vertices inside this geometry, it also has a measured value for the actual distance, which we're going to use for doing these validations. But for display purposes, what I can show you, I'm going to use this value just to kind of give us an idea of what those measures should be. Now, if we take a look at the tables, I have here an LRS table. Oh, wait 1 second. Well, let's do this. We have an LRS table, and in my LRS table, I have a route number, and we have a begin LRS value and an end LRS value. So this is the information that we can use for doing these validation checks. So what I'm going to do real quick is make sure that I'm at the right extent. We'll open up my widget that has my rules. Oh, let's move this over here. And I'll go ahead and process. I'm going to run my rules on this extent. So we have 6 different validation checks that we're doing here. The first validation check is, does the begin LRS actually exist on the route? So for example, this particular LRS record says the begin LRS is 0.16 for this route number. Does that actually exist within the 2 measure values? So we get the min and the max measure value and see if the begin LRS is within that range. We do the same thing for the end LRS. We make sure that the end LRS is within the min and the max value. By doing those 2 checks, we can determine whether or not this actual record exists inside the GIS system. We're also checking each individual route, making sure each individual route has at least 1 LRS record associated with it. Then we're looking for gaps in my LRS tables. So we're looking at seeing that is there a LRS record that's at the start of my particular line segment. So for example, in this case, this begin LRS is 0.16. Is there another record that's associated with this particular geometry that goes from 0 to 0.16? So that's what we're checking there. And then we're doing the same thing at the end. So if this says the end LRS is 0.19 and the max LRS for this record is, say, 1 kilometer, is there another record inside this database that goes from 0.19 out to 1 kilometer? And then lastly, we're checking to make sure that the routes are monotonic. That means that the measure values are increasing as you go to each individual measure value for a particular line segment. So now that we've run these rules, we can take a look at these results. So what I'm going to do is just to make this easier, let's just look at one of these at a time. So for this particular rule here, where we're checking to begin LRS, if I take a look at this particular line segment, this is for PR828. So let's take a look at PR828 in my LRS table. And if I look at the begin LRS and the end LRS for all the records, we have two records here. We have one that goes from 0 to 3, and another one goes 3 to 3.75. Well, if I look at this segment here, this segment is actually only 2 kilometers long. And so this, if we're looking at this record here, this one starts at 3 kilometers, which is outside that range from the beginning and the end measure values of this particular segment. That's why we're flagging that as a nonconformance. We should also see that we have the exact same issue at the end LRS also, because the 3.75 is also outside of that particular range too. If we take a look at the gap check, oh, I'm sorry, let's check this one real quick. We first want to check to see if where do we have, for all my routes, is there an existing LRS? So if I take a look at this particular segment here for PR612, so I'm going to go ahead and select this one, and let's filter this table this time to look at just that record. So I'm going to go ahead and check that. Notice how no records are being returned. That's saying, well, this is the reason why we're getting this nonconformance. But what's interesting is I'm going to just take a quick look and see, well, is there something similar to this? Maybe they were having some sort of weird issue. So when I select PR612, I can see that there is something coming back, but there's an empty space inside this particular value. So when I apply that check, we can see that we're getting back results. So what I want to do is I want to update my rule to make sure that I'm not missing the ones that have those empty spaces. So I'm going to go over to my rules engine. Here's the rule. We're saying for all my routes, there must be at least one LRS record where the street name is equal to the route ID. So we can come in here. We're just going to go built-in function. We're going to use a trim. And we're going to now select that particular record. So now it's going to trim that, so then it will no longer, it will catch all those other ones that have just that extra little space, the extra space in it. I'm not going to go ahead and run that rule again right now, but take me for my word that it won't flag that feature anymore. And then the last one is where the last two is where we're checking the LRS assets at the gap at the start or the end. So let's go ahead and flip that to the example here where we're saying the LRS has a gap at the start. If I select this feature, PR615, and I come in here and we're gonna say PR615, and I look at my begin and end LRS. Let's come over here. Where is it at? We can see the start is at 10.7 and the end is at 16.2. So there's that gap of 10 kilometers where there's no sort of LRS record at the beginning of the segment. Now, what's interesting enough is that this is the same issue that we just saw before. So if I come in here and I say PR615 and I select the one that has the gap, now when we check this, in this case, we should have 0 to 9 and 9 to 10.7. So we wouldn't have that gap if we also trim those values for doing that check also. And then lastly, let's go ahead and take a look at the end route. If I come over here and I select this particular feature. So for PR644, and let's apply that filter here. And if I look at these results, okay, so we have a begin LRS from 0 to 0.35, 0.35 to 1.25. Well, this segment here is at least 1.64 kilometers long. That's why it's being flagged as a nonconformance, because we have a gap, at least a gap from 0.25 out to 0.64. right? So there's a gap there. That's why it's being flagged as a non-conformance. So there's a whole different set of rules we can run to validate, your LRS system to your GIS system and your GIS system back to your LRS. So these are just a couple examples of ways to validate to make sure that they're correct. Other things we can do is a lot of times you may see that your GIS data has some sort of speed information in, like a speed limit information, and your LRS system may have pavement information, so that you can validate, well, is the pavement correct based off the speed limit, or I should say, is the speed limit correct based off of the pavement, depending on which one is the more authoritative data source or the more accurate data source. All right, so with that, let's go ahead and go back to my slides. And I can now answer any questions that may have popped up during the presentation, or Sheila, if you have anything you'd like to add, we can now take questions.
Yeah, we have just a few questions.
Okay.
So one of them is, I don't have these exactly in order, but can you validate polygon or boundary data?
Yes. So in this case, we did mostly just linear data because we were dealing with a lot of road centerline data. But in the beginning, if you remember, we also had those town boundaries. We could have checked to see if there were gaps or overlaps inside those town boundaries. We can check to see if points exist in polygons. So basically, the short answer is yes. We just didn't focus on that today.
Perfect. And can you integrate with GPS data to automate accuracy?
Yes. So say, for example, you are collecting data with a mobile device, and you have that connected to something like, say, a Trimble or some other type of antenna that gets you more accurate information. You can actually update the geometries to shift or align to those collection points. So you can define in the rules engine what the relationship should be, and it can auto correct that information. So, there's other examples of what we call position accuracy improvement, where you may have a more accurate data set that you want to align all your data to. So you can develop those shift vectors to align them.
Okay, great. And then can the rules be shared?
Yes. So when let me just show you that real quick. So 1 second, bear with me. Let me go back to my rules engine. So when we're in the rules engine itself, we can right click on the rule, download it. And now we have the rule set, so we can share it with whoever we want to share it with. We can just say somebody else created this rule set and they shared it with me. I then can go ahead and drag and drop that in. New rule. And now I have that updated rule set that was provided to me from a different user.
Great, and then we have just a couple more. One is there a limitation on the size of the database that you can work with?
No. So we've worked with data sources that are for example, we worked with one data source that was transportation data for the entire country, and we were able to run validation and conflation efforts on that entire data set. It took a few hours to run through, but we were still able to do a data set that was that large. So we don't have limitations to the size of the database. It's just basically how much disk space do you have on your disk to do those types of validations.
All right, and the last one was, does mobile just work with collector?
So no. So the mobile piece, this instance of the mobile piece, which is our one integrate for ArcGIS mobile edition, it works for collector for ArcGIS. It works for Survey 123, or anything that leverages an ArcGIS feature service. So if you had a third-party application that was bringing in that service, you can also apply it on those data sets. And that includes even in the web environment or your desktop environment. If you're accessing and editing those feature services, as those edits get posted up, it will do the validation. So it's not limited to just collector.
All right, wonderful. Well, that's all the questions that we have right now, but if you'll notice on the screen are both my email and Kevin's email are there underneath our names, Sheila.Stephenson@onespatial.com and Kevin.Sigwart@onespatial.com. And we would welcome any other questions you may have, or if you have a particular data challenge or something you'd like to see whether or not we might be able to show you whether the rules engine would be able to help you with those challenges, we'd be happy to do so. So please feel free to reach out to us. And we appreciate your time today. I think we're giving you about 5 minutes back, unless, Kevin, you have any last words.
Nope, I'm good.
Okay.
I'll take those
All right.
5 minutes.
Well, there you go. Thanks, everybody, for your time. We really appreciate it.